South Carolina is beautiful, and South Carolina Electric and Gas is working to keep it that way while ensuring a ready supply of electricity for today's needs. We are using new technology in making electricity. We're improving the efficiency of our generating plants, and we're building ahead today to provide electricity for tomorrow. And now, South Carolina Electric and Gas presents the Science Screen Report.
The Science Screen Report. Developments in science, engineering, and medicine that help solve the problems of modern life. Around the world today, computer-controlled industrial robots, together with computer-aided design, are being applied to manufacturing in ways that will profoundly affect our society. Benefits include safer working conditions, higher quality products, and more efficient use of resources. Benjamin Franklin called man the tool-making animal. Until 2 centuries ago, the tools were relatively simple, and nearly all were made by hand, one at a time. But in the 18th century, Franklin and his contemporaries linked science to technology and started the first industrial revolution. Power and dexterity were transferred from man to machine. Productivity rose as mass production became increasingly common. But not everything can be mass produced. In fact, most manufactured goods are made in batches of 50 or less. So what has long been needed are new production techniques for batch manufacturing jobs. These production techniques, a new phase of the Industrial Revolution, are now available thanks to the development of industrial robots. In general, such industrial robots are computer-controlled machines which monitor the quality of their work and are easily programmed to do a variety of tasks. But before the robots can manufacture a product, the parts must be designed. At the University of Rochester, researchers have developed a computer-aided design system to speed manufacturing via robots. These are the parts of a commercial vacuum pump. Formerly, before such a pump could be manufactured, the parts were designed and redesigned, then used to build prototypes. Eventually, the designs were refined sufficiently to be used to set up the batch manufacturing system. The new approach speeds both production and the time-consuming design process by immediately providing the robot's computer with accurate parts descriptions. The new system of designing parts is fundamentally different from drawing. Using a special computer language, a part is described by adding or subtracting simple shapes such as blocks and cylinders. For instance, one command is all that's needed to draw a block. To make a hole in the block, a cylinder is subtracted from it. On command, the computer moves the hole left center, adds another block, and so produces an angle bracket. Besides shapes, this system can also specify dimensions and tolerances. By doing more additions and subtractions of blocks and cylinders, it's possible to describe very complicated parts. Most important, descriptions given this way are complete, concise, and ideally suited to manufacturing systems that use robots. In most batch manufacturing, assembly and inspection still require human hands, eyes, and minds. A dull job that calls for intense attention. This is work ideally suited to industrial robots. Building the necessary sensing ability into robots is being done at Stanford Research Institute International in California. This experimental machine vision system can act as the eyes of a parts manipulating industrial robot. First, a programmer shows each part from several directions to a TV camera linked to the robot's computer brain. The computer extracts and stores the major features of each part's shape. Later, presented with a part, the computer compares it with those in its memory until it recognizes it. Soon, this system may enable robots to identify, inspect, and assemble parts into products automatically. Here, a similar machine vision system enables a robot to install a cover plate on a small engine, atop a computer-controlled movable table. The TV camera determines the proper position for the engine and bolt holes, then lines them up for the job. Meanwhile, the robot picks up a pneumatic wrench, gets a bolt from an automatic feeder, and starts the assembly. After each bolt goes in, camera and computer check that it's properly installed, then line up the next bolt hole. Other built-in sensors check that the bolts are properly seated and tightened. Such sensory intelligence systems already show high efficiency and adaptability. Ideally, batch manufacturing robots should be able to do all kinds of assembly work, knowing how and when to apply each different skill: welding, drilling, fitting together. One robot control program designed to accomplish this is called Hierarchical Control, developed by the National Bureau of Standards. Hierarchical control involves breaking down a job into a hierarchy of tasks, single motions which make up larger actions which lead to the basic goal. The robot is first taught the single motions or joint positions. Teaching the joint positions is tedious, but will only have to be done once. Following this, the joint positions are linked into larger actions via the single control lever. Last, the final goal can be taught, such as go to position 2 and grasp. Given such an order, the robot's computer carries out the simple steps involved by itself. But always remember, the robot is just a machine. It cannot think nor deal with situations for which it has not been programmed. To help compensate for these limitations, the robot projects beams of infrared light. These allow it to detect an object, a process known as sensory feedback, as revealed by the oscilloscope pattern. In this demonstration, the robot has been taught to do block stacking, a task requiring a very short computer program.
Now we have this robot connected up so it can talk. The computer which controls this robot is attached to another computer which controls a voice synthesizer which controls this loudspeaker and allows the robot to talk to you. So if you'll listen carefully, the robot will introduce himself and then he'll tell you what he's going to do.
I am a robot. I have 6 joints. I will move 10 one at a time.
Okay, that's one joint. He moves back and forth. Second joint, he moves up and down. Third joint, he reaches out there and grabs you by the nose. The fourth joint, the fifth joint, and the sixth joint.
Now I will move all of the joints at the same time. I will pick up these boxes from this table and set them on the other table.
Okay, now even if this box is a little bit out of line there, the robot will sense it and move over and find it.
I have found the box. Now I will pick it up.
Okay, now that was pretty easy. Let's see what the robot does if we take the box away altogether.
Someone move the box.
Now it searches for the box along the only place it knows to look for a box, which is right along this line.
Someone has taken the box.
It didn't find it. We'll put the box back, and it finds it.
I have found the box. Now I will pick it up.
Now we can steal the box away while it's not looking. And it'll notice.
I thought I saw a box here.
So it goes back and looks some more.
I have found the box. Now I will pick it up.
Now the robot's been programmed to stack this box on top of the other, so that if we move the other box, it looks for it and doesn't find it.
I thought I put a box on this table.
Looks some more.
I know I put a box here. Someone has taken it. Please put it back.
Finds the other box, moves over it, and sets it down.
I am finished. You may go now. Thank you for coming.
Hierarchical control is one more step in robot evolution, allowing the machines to carry out almost any clearly defined manual job. Slow and dull robots may be, but they have only evolved for a few decades. Their potentials have barely been tapped.
The Science Screen Report has been presented by South Carolina Electric and Gas Company, the company that is providing for today's electric needs while planning ahead for the future.